Hello, and welcome to the Sinha Foundation lecture series on classical mechanics. I'm Amit Sinha. In this lecture, we will start to think like a physicist. In 1949, the United States government was furious with a British physicist named G.I. Taylor. He had just published the yield of the Trinity atomic bomb test, a number that was still top secret. But Taylor hadn't stolen anything. All he used was a photograph from a magazine, a ruler, and one idea so powerful it feels like cheating. That idea is the subject of this entire lecture. Before we touch a single law of motion, I want to hand you the three tools that separate people who memorize physics from people who can actually do it: dimensional analysis, Taylor expansions, and limiting cases. Along the way, we'll weigh a blast, jump a flea, drop a mouse, swing a pendulum, and find Newton hiding inside Einstein. Let's go. Every quantity in mechanics is built from just three ingredients: mass, length, and time. Force, energy, pressure, momentum, they're all just packaging. Force is mass times acceleration. Mass is m, and acceleration is length per time squared. So force is mass, length per time squared. Energy is force times distance, one more factor of length. We write these building blocks in square brackets, m, l, and t. Here is the rule that gives this teeth. Any equation in physics must have the same dimensions on both sides. Always. You cannot add a length to a time any more than you can add 3 meters to 5 seconds. It sounds obvious, but it is a merciless error detector. Let's test it on something familiar: the distance fallen from rest, x equals 1/2 gt squared. G carries dimensions of length per time squared. Multiply by t squared and the time dimensions cancel completely, leaving pure length. The left side is the length. It checks. Notice what the check ignores: the 1/2. Dimensional analysis is blind to pure numbers. That blindness is the price we pay, and you should always remember it. But everything else about an equation's structure, it sees with X-ray vision. Now let's turn the error detector into a prediction machine. Here's the recipe. Step 1. List every quantity the answer could possibly depend on. Step 2. Find the combination of those quantities that has the dimensions of the thing you want. Step 3. Write down the answer times some unknown pure number, which is usually close to 1. Watch it work. Drop a rock from height h. How long until it lands? The fall time can only depend on h, on gravity g, and maybe on the mass m. Try to build a time out of these. G has length over time squared, so h over g has time squared, and the square root of h over g is a time. And here's the beautiful part: the mass never fits anywhere. There is no way to include m and still get a pure time. Dimensional analysis just told us that heavy rocks and light rocks fall at the same rate. Galileo, in one line of algebra. One more, because this trick feels like magic. What sets the speed of a long ocean wave? Think about what the water knows. Gravity g pulls the surface back down, and the wavelength lambda sets the size of the disturbance. For long swells, that is the entire list. Build a speed. G times lambda carries dimensions of velocity squared. So the wave speed is the square root of g. Lambda times a number near 1. Longer waves travel faster. That is why the long, slow swell from a distant storm arrives at the beach a day before the storm itself. The ocean does dimensional analysis for free. Back to the bomb. A nuclear explosion dumps an enormous energy, E, into the air, and a shock wave expands as a glowing fireball. The magazine photo showed the fireball at a radius of roughly 140 meters, 25 milliseconds after detonation, with a helpful scale bar printed right on it. What could the radius possibly depend on? The energy E, the time T, and the density of the air ρ. That's the complete list. Now play the game. Build a length out of ET and ρ. Energy is mass, length squared, over time squared. Density is mass over length cubed. Divide E by ρ and the mass cancels, length to the fifth over time squared. Multiply by t squared, take the fifth root. The radius must be ET squared over ρ all to the 1/5 power times a number near 1. Solve for E and put in the numbers. Air density about 1.2. Radius to the 5th power over time squared. Out comes 10 to the 14 joules, about 25 kilotons of TNT. The classified answer was around 20. Taylor got within 20% of a state secret using a ruler and freshman physics. Now, something lighter. Why can a flea, a frog, a house cat, and an Olympic athlete all jump to roughly the same absolute height within a factor of a few when their masses span 9 orders of magnitude? Take any animal and scale every one of its lengths by a factor L. Muscle force grows like cross-sectional area, L squared. The work a leg does in one push is force times leg length, L cubed. But the mass being launched also grows like volume, L cubed. Jump height is energy over mg, so the L cubed on top cancels the L cubed on the bottom. Jump height is independent of size. The scaling argument doesn't care whether you're a flea or a kangaroo, and neither does the meter or so of height you get. Same scaling. Opposite headline. Why can an ant carry 50 times its own body weight? Strength comes from muscle cross-section, L squared. Weight comes from volume, L cubed. So the ratio of strength to weight scales like 1 over L. Shrink an animal and it becomes a superhero. Grow one and it buckles. An elephant cannot jump. Its bones already spend most of their strength just holding it up. And the giant ant of the comic books would collapse under its own weight the moment it stood. Scaling laws, not effort, write the rules of the animal kingdom. This one saves lives, at least for mice. Falling through air, the drag force grows like the density of air, times speed squared, times cross-sectional area. Terminal velocity is where drag balances weight, where you stop accelerating, and weight grows like volume, L cubed. So terminal velocity squared goes like volume over area. 1 power of size, terminal velocity grows as the square root of L. A mouse falls slowly enough to walk away. A horse does not. Haldane said it best: you can drop a mouse down a mine shaft, and on arriving at the bottom, it gets a slight shock and strolls away. Now, the pendulum, a mass m on a string of length L, swinging under gravity g released from some angle, theta naught. What is the period? Let's think like a physicist. The period could depend on m, on L, on g, and on the amplitude theta naught. Build a time. Mass, just like the falling rock, there is nowhere for it to go. Nothing else in the list has mass in it, so m cannot appear. The square root of L over g is a time, so the period must be some pure number times the root of L over g. The true answer, which we'll derive properly in a few lectures, has that number equal to 2 pi. But wait, what about the amplitude? Here's the subtlety. Theta naught is an angle, a ratio of lengths, so it's dimensionless. Dimensional analysis can't see it. The period could in principle be any function of theta naught, and dimensions would never complain. So is the pendulum period actually amplitude independent? Almost. For small swings, yes, and that's why pendulum clocks work. The first correction turns out to be theta naught squared over 16. At 10 degrees of swing, that's about 0.2%. Dimensional analysis drew the map. The fine print needs a sharper tool. That sharper tool is the Taylor series, and I want you to think of it as the physicist's microscope. Zoom in close enough on any smooth curve, and it looks like a straight line. Zoom with a bit more care, and it looks like a parabola. 4 expansions will run this entire course, so let's watch each one converge. Start with sine. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Watch the terms work. One term is a straight line. Add the cubic and the polynomial hugs the curve. Add the 5th power and you can barely tell them apart. Cosine plays the same game. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And the binomial 1 plus x to any power n is 1 plus nx plus n minus 1 x squared over 2 factorial, and so on. That innocent rule will unlock relativity in a few minutes. Finally, e to the x, 1 plus x squared over 2 factorial, and so on. Term by term, the polynomial becomes the function. Poked gently, almost everything behaves like a straight line. That is why small oscillations are simple, and why the harmonic oscillator rules the universe. And this one is a beauty. Einstein defined the energy of a moving particle as gamma mc squared, where gamma grows without bound as the speed approaches the speed of light. Newton said kinetic energy is 1/2 mv squared. These two look like they come from different planets. Taylor says neighbors. Call the small parameter y v squared over c squared. For a jet plane, y is about 10 to the minus 13. Gamma is 1 over the square root of 1 minus y. So our 1 plus x rule with n equals minus 1/2 expands it 1 plus y over 2 plus 3y squared over 8. Now multiply through by mc squared and watch what falls out. First, mc squared, the rest energy, there whether you move or not. Then, exactly 1/2 mv squared. That term is Newton's kinetic energy, hiding inside Einstein's formula as the first Taylor correction. Newton wasn't wrong. Newton is the small velocity limit of Einstein. That single sentence is the deepest thing in this lecture. So how small is small? Put in numbers. A car on the highway, v squared over c squared, is about 10 to the minus 14. A passenger jet, 10 to the minus 13. The space station, the fastest thing humans ride, about 6 times 10 to the minus 10. That is why Newton ruled unchallenged for 2 centuries. Below a tenth of the speed of light, the corrections are invisible. But the electron beam in an old television tube runs at a third of the speed of light, and there the next Taylor term decides whether the picture is sharp or smeared. When the small parameter stops being small, keep more terms. Tool number 3. Limiting cases. After you solve any problem, push every parameter to its extremes and ask whether the formula does something sensible. This costs you 30 seconds and catches half of all algebra mistakes, which is the best deal in physics. Take a result we will learn soon. The Atwood machine, 2 masses on a pulley, accelerating at the mass difference over the mass sum, times g. Check 1, equal masses. The difference vanishes. The acceleration is 0. The machine balances. Good. Check 2, m1 goes to 0. The formula says A goes to G. The heavy side is in free fall, dragging a massless partner. Good. Check 3. M2 enormous. The acceleration approaches g but never exceeds it. And if your derivation had produced the sum on top instead of the difference, check, one would have exploded the mistake instantly. That is the whole tool. 30 seconds of limiting cases after every derivation, and half of all algebra mistakes never survive to the next line. Step back and look at what just happened. We weighed a nuclear explosion, explained the animal kingdom's jumping records, computed a pendulum period, and unified Newton with Einstein without solving a single differential equation. Dimensions fix the structure of every answer. Taylor expansions reveal what hides in the small corrections. Limiting cases are the free error check you run on everything, forever. From now on, every result in this series gets this treatment automatically. Derive, then check the dimensions, then push the limits. It will feel like a habit within 3 lectures. It will feel like a superpower within 10. Before we close, one problem where all 3 tools fire in sequence, the tsunami. Water waves obey an exact law. V squared equals g lambda over 2 pi times a function of the depth d over the wavelength. Dimensional analysis built the front factor for us earlier. The tangent factor is exactly what dimensions cannot see, a pure function of a dimensionless ratio. Now, Taylor. A tsunami is hundreds of kilometers long, crossing an ocean 4 kilometers deep, so d over lambda is tiny, and tangent of a small number is just that number. The wavelength cancels and the speed collapses to the square root of gd. Put in 4,000 meters, 200 meters per second. A tsunami crosses the Pacific at the speed of a jet airliner. Finally, the limits. Deep water, tangent goes to 1, and we recover the swell from earlier, speed set by wavelength. Shallow water, speed set by depth alone. So, as a tsunami runs ashore and d shrinks, it slows, the back catches the front and the wave rears up. Derive, expand, check the limits, one formula, the whole toolkit. Next time, we put these tools to work on real machinery, ropes, pulleys, friction, and the surprisingly deep physics of things that refuse to move, statics. That wraps up this lecture. This is Amit Sinha. Thanks for watching the Sinha Foundation channel. See you in the next one.